Hello, I want to start a series where I want to show the progress of my polyphonic synth controller. What we have to talk about? We have to talk about intervals, we have to talk about frequency ratio, and we have to talk about a simple VCO. Let's start with the simplest interval. This is the octave. The frequency ratio of A3 and A4 is 2 to 1. This means that the A4 with a frequency of 880 Hz is twice in the frequency of A3, which is 440 Hz. The smallest interval is a semitone. The frequency ratio between two halftones is 1.05946 blah 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 to 1, which means if you multiply the frequency of B with this factor, you will get the frequency of C. In this table, you can see the frequencies between the key C3 and C4. If you multiply the frequency of C with this factor, you get the result of the frequency of C sharp. If you multiply the frequency of C sharp with this factor, you get the frequency of D3. If you do this 12 times, you get the frequency of C4. So you have done a complete octave jump. In this diagram, you see the relationship between the notes and the frequency. The notes are on the horizontal axis and the frequency is on the vertical axis. As a result, we get an exponential graph. What is a voltage-controlled oscillator? A VCO is a circuit which generates an audio signal. The waveform of the audio signal depends on the circuit. The circuit details are not relevant now. The output frequency follows the voltage at the input. The VCO usually has a linear characteristics. This is a simplified block diagram of the signal or tone generation in a synthesizer. Here we've got the voltage source. Normally this is a keyboard or the MIDI interface. This is a voltage-controlled oscillator which generates the tone signal. And this is an audio amplifier where you can plug in your headphones or some speakers to hear the audio signal. As I told earlier, a VCO usually has a linear characteristic. If there's 1 volt at the input, the frequency in this example is 110 Hz. If you put there 2 volts, you will get 220 Hz. If you put in 3 volts, you get 330 Hz. If you put in 4 volt, you get 440 Hz. In this diagram, we see the relationship between the voltage at the horizontal axis and the frequency at the vertical axis. In this case, we see this is a linear relationship. So, what's the challenge? The challenge is to transfer the musical exponential curve into the linear VCO world. So, how could this be done? This could be done by creating an exponential control voltage and using a linear VCO, or creating a linear control voltage and using a VCO with a kind of linear to expo converter. Let's start with version A. In version A, we divide our voltage source in 2 parts. Part 1 is creating the voltage for the octaves, and part 2 is creating the voltage for the semitones. After this, there's a VCO and the audio amplifier. The first part creates the voltage for the octave range. The frequency ratio is 2 to 1, so the voltage ratio is also 2 to 1. If we want to have a C3, we need an input voltage of 0.5 volt. If we want to have a C4, we need 1 volt. If we want to have a C5, we need 2 volt. And if we want to have a C6, we need 4 volt. The second part is responsible for the semitones. The frequency ratio between two semitones is 1.0594 to 1. So the voltage ratio is also 1.0594 to 1. In this table, you can see here the keys, the corresponding frequencies, and here our well-known factor. We use 1 volt for generating the frequency of a C3. If we multiply this 1 volt with our factor, we get the control voltage for the C sharp. If we multiply the control voltage of a C sharp with this factor, we get the control voltage for a D3. So if we do this 12 times, we end in the 2 volt, which is the corresponding control voltage for C4, which is our octave jump. In this diagram, we see here the keys on the horizontal axis, and we see here the control voltage at the vertical axis. And this results in a nicely exponential graph. Now it's time for a summary. As we can see, it is a multiplication of the octave voltage and the node voltage. So in this example, our factor is 130.8127 Hertz per volt. A control voltage of 2 volts results in a frequency of 261.6254 Hertz. Now it's time for the volt per octave version. At this method, 1 volt represents an octave. For example, the input voltage of 1 volt creates a frequency for C3. The input voltage of 2 volt creates C4, 3 volts C5, 4 volts C6. And one semitone is 1 volt divided by 12. In this table, we see here the keys, the corresponding frequency, and here we start with a control voltage of 2 volts. If we add this 0.0833 volt, we get the control voltage for the C sharp. If we do this again, we get the control voltage for the D3. If we do this 12 times, the result is 3 volts, which is 1 volt higher than 2 volt. And this corresponds to an octave jump. So in this diagram, here we've got the nodes, and on the vertical axis we've got the control voltage, and as expected, the graph is linear. So here we can see it is an addition of the octave and the node voltage. Because the control voltage is linear, we have to do some changes in our circuitry. We don't need the semitone control voltage circuit anymore. We put them both together in one linear control voltage stage. But therefore, we need a linear to exponential converter to get the correct exponential frequency. So, both systems have their pros and cons. Here's the pros and cons of the Hertz per voltage system. The pros are you can use a simple VCO design, you have a high linearity, and the VCOs are very temperature stable. The cons are creating the exponential control voltage is more complex. Interval shift has to be done by a multiplication. And here are the pros and cons of the volt per octave system. The pros are creating the linear control voltage is easy. Interval shift is done by an addition. The cons are building an expo converter is complex. The linearity is not so good. Temperature stability is hard to obtain. So, it's time for a summary. The volt per octave system is a standard. It is used in almost every modular synthesizer and also used in the most monophonic analog synths. The Hertz per volt system is used in some monophonic synths. In my opinion, the Hertz per volt system is a good solution to build a polyphonic synthesizer. You can build easy and stable VCOs, and this counts in polysynths. You lose some versatility, but this is the domain of the modular synths. In part 2, I will show a Hertz per voltage digital to analog converter with discrete resistor networks. Thanks for watching. Bye.